In the last lecture, we introduced the concept of electric dipole and found the electric field due to an electric dipole. In this lecture, we start with finding the electric potential due to a dipole. You see, this is a dipole here, plus q minus q, and P is a point on the equatorial line at a distance r from the center of the dipole. So, what we do is find the potential at P due to q, which is q by this distance, and then minus q, the potential at P is minus q divided by this distance, and since these two distances are equal and these are two opposite charges, therefore, the potential at P is equal to 0. But the electric field, as we found in the last lecture, at P is not equal to 0. The electric field is in this direction, whereas the potential is equal to 0. Now, we take a point along the axis of the dipole, say P, and this distance r is equal to, this distance is r plus a, and this distance from this point is r plus a, and this one from here to here plus q to P is r minus a. So, therefore, the potential due to plus q is q by 4 pi epsilon 0 1 by r minus a, and due to charge minus q, it is q by 4 pi epsilon 0 with a minus sign into 1 by r plus a. So, we add them and we find the potential. The potential is 1 by 4 pi epsilon 0 P by r squared in the limit in which a is much less than r, and 2 a q as before is equal to P. So, the potential due to this dipole moment P is 1 by 4 pi epsilon 0 into P by r squared. Similarly, we can find the potential at any point P. Suppose the coordinates of P are x and y. So, we erect a coordinate system. This is x axis, this is y axis, and the coordinates of point P are x and y, and these distances from plus q to P is r 1, from minus P to P is r 2. r 1 we can find in terms of x and y, r 2 we can find in terms of x and y, and we shall expand them. The potential is of course 1 by 4 pi epsilon 0 into q into 1 by r 1 minus 1 by r 2. So, we know r 1 r 2 in terms of x and y and a. So, we expand 1 by r 1 in the limit of a much less than r, and we get 1 by r 1 is 1 by r into 1 plus y a by r squared. Remember, y is this and x is this, the coordinates of P are x and y, and similarly 1 by r 2 we expand in the same limit and we get this, and we substitute them back into this equation and we get the result. Ultimately, you can the result is phi equal to q by 4 pi epsilon 0 2 y a by r cubed, and this y by r is sine of this angle, which is cosine of theta. So, y by r is cosine theta, and we substitute and we get phi equal to P by 4 pi epsilon 0 r squared into cosine theta. And in terms of vectors, since r cap is a unit vector, so we can write cosine theta as P vector dot r cap and divide by 4 pi epsilon 0 r squared. So, that is the potential at any arbitrary point. The expression contains both the results. This expression, I mean, if you put theta equal to 90 degrees, you will get the result for the equatorial line, and if you put theta equal to 0, you will get the result for the axial line. And important thing to notice is that the potential due to a dipole varies as 1 by r squared, whereas if you remember the expression for the electric field, it varies as 1 by r cubed. Now, suppose we place this electric dipole in an electric field. In this diagram, electric field is uniform, direction is from say left to right, and we place a dipole with plus q here and minus q here, dipole moment in this direction from minus to plus sign, and what happens? This plus q moves because of the electric field, it feels a force in this direction. This minus q feels a force in this direction. These two forces are equal, because the charges are equal and they are opposite. So, they form a couple. And what is the moment of the couple? The perpendicular distance is 2a sin theta, where theta is this angle, and therefore, the magnitude of the couple is the one of the forces into the arm of the couple. And so, the couple is 2a sin theta dot QE, QE is the force and 2a sin theta is the arm of the couple, and therefore, this is PE sin theta. 2aq remember is P. So, therefore, it is PE sin theta. And since I have told you already that P is a vector quantity, E is also a vector quantity, torque is also a vector quantity. Therefore, this expression Pe sin theta suggests that in vector notation torque would be P vector crossed with E vector. The torque is perpendicular to both P and E. You can see that the cross product is perpendicular to both P and E. And in this case, you can see that this tends to rotate the dipole in this direction, in the clockwise direction, so that it becomes parallel to the original direction of the dipole. Since it comes back to the original position of the dipole, this position of the dipole, that is pointing along the lines of force, is the position of stable equilibrium. And we know the definition of stable equilibrium. If I displace the dipole slightly from this position, it comes back. We have seen here that a couple comes into play, which tends to rotate it in the direction, clockwise direction, and brings it back to the original position. On the other hand, if the dipole is placed at an angle of 180 degrees, that is, its axis or dipole moment is anti-parallel to the electric field, then what happens? This is a position of unstable equilibrium, because now the couple will act such that it will keep on rotating the dipole, so that it does. Now, if I have a dipole and displace it slightly, it will keep on rotating till it becomes, the dipole becomes parallel to the electric field from the anti-parallel position. Therefore, this position is unstable equilibrium. We have seen when a dipole is parallel to the lines of force and it is displaced slightly, then it goes back. Does it form simple harmonic oscillations? Let us see. See, the torque acting on it is Pe sin theta, which for small theta is Pe theta. If I is the moment of inertia of the dipole, then the torque trying to bring the dipole back, you see, remember that this was the position of the dipole, I displaced it slightly and then it is tending to go back. So, this torque which brings it back is I times theta double dot, I times d2 theta by dt square, and no, the acceleration, the angular acceleration is proportional to the angular displacement. That is the signature of a simple harmonic motion. So, it performs simple harmonic motion and the time period is 2 pi square root of moment of inertia divided by Pe. The work done by the torque on the dipole to rotate it through an angle d theta is tau d theta, you know from mechanics. So, dw, the work done, is Pe sin theta. Pe sin theta is the torque and d theta is the displacement. So, it is the work done, and I can integrate from 0 to theta. So, that the work done when it is moved from an angle 0 to an angle 90 degrees or angle theta is Pe into 1 minus cos theta. Integral of this is Pe into 1 minus cos theta. This work becomes the potential energy of the dipole, and you remember that we can fix the 0 of the potential. So, for convenience we fix the 0 of potential energy at theta equal to 90 degrees. When theta is 90 degrees, so this vanishes. So, the potential energy at an angle theta, it may be written as Pe minus Pe cos theta minus Pe. So, it is minus Pe cos theta is P dot E. That is the potential energy of the dipole when it is displaced through an angle theta from the original position. Remember that we can choose the 0 potential energy. I have explained this to so many times, because it is the potential difference that matters. So, 0 does not matter. So, the work done is minus P vector dot E vector. This becomes the potential energy of the dipole when placed in an electric field. Clearly, the state of minimum potential energy is when the dipole is aligned with the field. The position of stable equilibrium is one where the potential energy is the least. So, when the dipole is aligned with the electric field, if the electric field is like this and dipole is also like this, then it is the position of minimum potential energy. And if the field is this and the dipole is this, then the potential energy is maximum. In general, the potential energy in a rotation from theta 1 to theta 2 is P e sin theta d theta integrated from theta 1 to theta 2, which is minus P e times cos theta 2 minus cos theta 1. Electron volt is an important quantity, and we use it very often in electric field and atomic physics and so on. And what is this electron volt? Electron volt is the increase in the energy of an electron when an electron moves up through a potential difference of 1 volt. The electron moves in the opposite direction to the electric field. When it moves up by 1 volt, then the work done is energy, that is called electron volt. So, electron volt is Q times the potential difference, which is 1 volt. So, if you multiply these two, you get this. So, 1 EV, 1 electron volt is 1.6 10 to the power minus 19 joules. And then we have KeV, which is 10 to 3 times the electron volt. We have MEV, which is 10 to the power 6 times the electron volt. We have GeV, which is 10 to the power 9 times the electron volt. We have these units for, and these are units used in atomic physics. And express the mass of an electron in units of EV. Mass of an electron, from the mass energy principle, the energy is mc squared, and the mass is therefore E by c squared, and therefore we can write mass equal to 9.1 10 to the power minus 31 kilogram into c squared, 9 into 10 to the power 16, and this is in joule. This we can convert into the electron volts, and we find that the mass of an electron in terms of electron volts is 0.511 MeV. Now, we shall do a few problems using the principles of electrostatics that we have learned so far. Here, two charges minus q each are fixed at a distance 2d apart. A third charge of charge capital Q and mass m is placed at the midpoint between the two charges, is displaced slightly. I will show you the diagram. Here we have minus q, this charge plus q was placed here, and I displaced it slightly in this direction. So, the displacement is in this direction. Now, if you find the force due to this and force due to this, what will happen? These components, this component perpendicular, this component perpendicular, they will cancel. Only this component towards the original position will remain. You can see that the condition for the simple harmonic motion is being satisfied. The displacement was in this direction, the force to bring it back is in this direction. Therefore, the condition for the simple harmonic motion is satisfied, and therefore, this charge will execute simple harmonic motions. So, all that we need to do is to put numbers and find the time period. I have done here, and you can see the acceleration, which is the force net force divided by m, and this cos theta is y by d square plus y square under root. I am using this geometry, and therefore, the acceleration is proportional to the displacement y, and it is in the opposite direction, and therefore, the charge will execute simple harmonic motions, and the time period would be given by 2 pi into 4 pi epsilon 0 m d cubed by 2aq. Take another example. A copper ball of density 8.6 gram per centimeter cube, 1 centimeter in diameter, is immersed in oil of density 0.6 gram per centimeter cube. The charge on the ball is 10 pi by 3 microcoulomb, plus it is a plus sign. What should be the magnitude and direction of the electric field if the ball is to remain suspended in oil? So, let us look at the free diagram. Let us look at the forces. Field is in this direction. Therefore, this ball will experience a force in this direction. There is also the force of buoyancy in this direction. The force due to gravity is in this direction, and if we balance the upward force, the downward force, the ball will remain where it is. So, it will remain suspended. So, that is all we have to do. So, we have QE, the force upwards, then this is the force of buoyancy, 4 pi r cubed times rho oil, that is the mass of the displaced oil, into g. So, weight of the displaced oil. So, this is the force acting upwards, this is the force acting downwards, 4 by 3 pi r cubed rho copper, that is the mass of the ball, into g is the weight of the ball. So, you balance these and you can find out the strength of the electric field. Now, we have another variation. Each of the 8 identical droplets of oil is charged to 10 V, 10 volts. They merge into one single drop. Find the potential on the large drop. So, we have 8 small drops, they merge and they form a big drop. So, we have to find the potential due to the large drop. The potential on the small drops is 10 volt each. So, we can find the charge on each small droplet. 1 by 4 pi epsilon 0 q by r is the potential, that is equal to 10 V, r is the radius of the small ball, and therefore, charge is 10 into 4 pi epsilon 0 times r, and for 8 it is 80 into 4 pi epsilon 0 r, that is the total charge. The radius r, if I merge the small droplets into a big drop, what has happened? The volume of the small balls is 8 times 4 pi by 3 small r cubed. The volume of the large ball is 4 pi r cubed, 4 pi by 3 r cubed. If I equate the two, we get capital R equal to 2 r, that is the large ball has a radius which is equal to twice the radius of the small droplet. So, the potential on the big drop is 1 by 4 pi epsilon 0 capital Q by 2 r. Substitute the value of Q and you will get the result. You see, I have chosen a variety of examples. You see, none of these examples is of the same kind, they are of different kinds. Why? Because I want you to understand the principles of electrostatics, and I am trying to illustrate those principles by different examples. All these examples are different from one another. In this case, we have two metal spheres of radii r1 and r2. They carry charges q1 and q2 respectively. When they are connected by a conducting wire, find the potential of the sphere with radius r1. We denote k by 1 by 4 pi epsilon 0. So, we have two spheres, metal spheres, and then we connect them. When we connect them, what will happen? The charge will flow from one to the other till the charges are equal, because till the potentials are equal. The potential of one is q1 by r1, the potential of the other is q2 by r2. We connect them so that the potentials become equal, and when the potentials become equal, then we can find the potential on the sphere of radius r1. How do we do that? Initially, the potentials of the two spheres are k times q1 by r1, where k is this, and on the other this must be k q2 by r2. When they are connected by a conducting wire, the charge flows from the sphere at higher potential to the one at lower potential till the potentials are equalized. Suppose the sphere of radius r1 gains charge q. If it gains charge q, the other one will certainly lose charge q, because the charge is conserved. So, since the potentials have been equalized, we have k q1 plus q, this gained charge q, q1 plus q by r1 is equal to k times q2 minus q, because this lost the charge q by r2. So, we solve this equation for q and we have q equal to this. This is the charge on each sphere, and the substituting this value of q in k q1 plus q, q1 plus q by r1. So, we get the potential. Q we know, q is this, q1 plus q by r1. The potential on the sphere of radius r1 would be k times this, q1 plus q2 by r1 plus r2. And since the potentials were equalized, the potential on the other sphere should also have this value. You can verify. All that you do is substitute the value of q from here in this, and you will get this result. Another example, two identical metal spheres have charges q1 and q2. They are separated by a distance r. Then they are made to touch each other and separated again by the same distance r. Show that the force between them now is greater than that before. See, you understand the problem. We have two metal spheres, they carry certain charge q1 and q2, they are identical, same radius, and then they are made to touch. When they are made to touch, and then they are separated again by the same distance. So, we have to find the force initially and force finally and show that the final force is greater than the earlier force. Since the spheres are identical, the charge on each becomes half of q1 plus q2 when they touch each other. So, the force initially is k q1 q2 by r squared. You remember k is 1 by 4 pi epsilon 0. Force finally is k by 4 r squared into q1 plus q2 whole square, because q1 by plus q2 becomes the charge on each. To find the relative magnitude of the two, q1 plus q2 by 2. So, there is a factor of 4 here. q1 and q2 are charges on each. When they are joined, the charge on each becomes q1 plus q2 by 2. So, the force between them is k by 4 r squared into q1 plus q2 square. So, we find the difference ff minus fi, and we can show, if I use this strategy, 1 by 4 q1 plus q2 square minus q1 q2. We are finding this minus this, and this can be written as this or this, which is always a positive quantity. Therefore, this minus this is always a positive quantity. That means, this force is larger than this force. A positively charged particle is launched in an upward direction at an angle to the horizontal. This, you see, we have a positively charged particle and I throw it like this, like a trajectory of the projectile. We will find that this trajectory has to be that of a projectile. So, this is the velocity. Electric field is like this. I can resolve this velocity into two components, one along the field and another perpendicular to the field. Perpendicular to the field, there is no force. Along the field, there is a force. So, what will happen? The perpendicular component will decrease as it goes up, because it is decreasing. At some place it will become 0 and then start coming back. In the meantime, because of horizontal velocity, the particle keeps going. So, you can see this is the same situation as that of a projectile. So, the motion would also be that of a projectile. The path taken would be that of a projectile. So, in this lecture, we did several problems, or variety of problems in fact, to make you understand the principles of electrostatics. We also found the potential due to the dipole, electric dipole. We found when dipole is placed in an electric field, what is the work done in it, and that the direction, if the direction is parallel to the electric field, it is the direction of stable equilibrium. If I displace it slightly, then it comes back and performs simple harmonic motion. On the other hand, if the direction is anti-parallel, this is the electric field, this is the direction of the dipole, then if I displace it slightly, it just keeps on rotating till it becomes parallel to the electric field. So, this is the position of stable equilibrium, this is the position of unstable equilibrium. So, if I disturb, it comes back to the position of stable equilibrium. In the next lecture, we shall proceed with the Gauss theorem, which is very important, as you know.